Okay, and Jyotisana here will be talking about non-invasive estimation of moisture content in mushrooms using hyperspectral imaging and machine learning-based stacking regressive model. Really interesting. So over to you. Do you want to put that in? Because that will be easy for people to. Thank you. Over to you.
Hello?
Yeah.
Am I audible?
Yeah. Yeah.
Okay, very good afternoon, everyone. My name is Jyotsna Meena. I am from Indian Institute of Technology, Madras, Chennai, Tamil Nadu, India. Today I am going to present my work, which title is Non-Invasive Estimation of Moisture Content in Mushrooms using Hyperspectral Imaging and Machine Learning-based Stacking Regression Model. This work is also co-authored by Dr. Sujata Narayan Unni. So first, I will just give brief introductions about the mushrooms. So in worldwide, around 2,000 species of mushrooms is available. In that only some of the species are edible, such as oyster mushroom, shiitake mushroom, magical citrus mushroom. So mushrooms is a highly consumed in worldwide because it has easy harvesting and the lower prices. Mushroom is also very popular food among vegetarian and the vegan people because it has high nutrient value, it has a low carbs, low fat, and high protein and microbiome content and the nutrition. It is also called, it has also some bioactivities as a therapeutic food which prevents diseases such as cancer, hypertension, blood pressure, and sugar. Even all these advantages, mushroom has some limitations such as it is a very less shelf-life, 3 to 4 days in ambient temperature, and around 8 to 9 days in a refrigerated condition. So these are the methods available to check the quality of the mushrooms and to prolong the shelf life of the post-harvested mushrooms. So the traditional methods are like thermal, chemical, and physical. In thermal method, we are using some cooling and drying process to reduce the moisture content in the mushroom and to prolong the shelf life. In chemical method, we are using different kind of edible coatings outside the mushroom or some chemical washing and the electrolyte water to reduce the moisture content and to prolong the shelf life. In physical method, also we are using some kind of radiations or some electric field to increase the shelf life. And there are, but these methods also affect the quality, taste, texture of the mushrooms, and these are time-consuming, tedious, and also require expertise to use these methods. There are some intelligent evaluation methods such as hyperspectral imaging, multispectral imaging, artificial intelligence, deep learning, machine learning. You can also use Internet of Things to predict the quality of mushroom and different other parameters. Also, we can also predict the moisture content of mushrooms, and we can also identify we can also predict the shelf life of the mushrooms. So as in my previous slide, I also gave the introduction about the mushrooms and its shelf life. So moisture is a significant factor that affecting the deterioration of fresh mushrooms. So the high moisture content affect the quality and marketability of the post-harvested mushrooms. So therefore, monitoring moisture content value significantly evaluates the actual quality and shelf life of the mushrooms. So before consumption or the processing. So in this paper, we propose the stacking regression model to accurately predict the moisture content in mushrooms from hyperspectral imaging data as a pre-screening tool for fresh food before deterioration. So the performance of the stacking regression model we also compared with the available existing state-of-the-art methods reported in the current literature. So we have developed two models. First we call it stack regression model 1 and the second we call as stack regression model 2. So stack regression model is a combination of two layers, the base layer and the final layer for stack regression model 1. We use Bayesian regression and the linear regression as the base estimator or random forest regression as the final estimator to predict the moisture content of mushroom. In a stack regression model 2, we use same Bayesian regression and linear regression for the base estimator, and in place of random forest regression, we use artificial neural network as the final estimate. So for these models, we use publicly available spectral food data set. So the data set was collected using the active micro hyperspectral imaging camera, which is not visible to NIR range. The spectral length 204 it has 204 spectral bands and a 7 nanometer spatial resolution. The images of the mushrooms captured from 7 nanometer distance from the sample and the so the used data set contains the average mean, the reflected spectrum or 250 sample images of mushrooms with the corresponding moisture content. So to calculate the moisture content value, they use the old air dried method to write the mushrooms and calculating the moisture content using the given formula. So for experimental purpose, we divided the dataset into two dataset A and dataset B. So dataset A contains the 80% of the total strata and remaining 20% we allocated to the dataset B, which used as unseen dataset to check the model generalization capability in the future. We also to evaluation method for evaluation of our dataset we use Stanford cross validation. So here table 1 reported the performance of the stack regression model 1 and stack regression model 2. So stack regression model 1 performs better for dataset A with Stanford cross validation score, and we got R-star value at 95.2%, and for unseen dataset B we got 96.2%, and similarly for stack regression model 2 we got 90.54% R-square and for dataset A and 93.2% on dataset B. Okay, we also compared our proposed model with the available literature method, and still our model performed better compared to the existing method. And we also have done the ablation study to show the significance of the standing regression model on dataset A, and table 3 reported the results of the individual model and the state regression model, and the results which we got better is for standing regression model. This table is showing the significance of the static regression model for predicting the moisture content in mushrooms. The table 4 is showing the some of the instances where our model got failed. So where the percentage difference between the actual moisture content value, the predicted moisture content value is highly differs around 56.48%, and the minimum is around 0.01%. So we didn't get any external data sets to check the model generalization capability. So for that we added noises in the unseen data set B. So for that we assume that this is approximately normal. Unseen data set B has a normal approximate normal distribution. So we added noises from the standard normal distribution by varying the standard deviation. So for that, when we are adding the significant amount of noises, the model is performing better, still better. We are getting around 93.8% RT score. And when we are increasing the noises, the performance is little bit decreasing, like around 72.87. But when we are adding more noises, more than the significant amount of noises, it is reducing the model performance. So with this, we also inferred that when we are capturing the images, the different cameras, so there will be variation. Both cameras, the model is still performing better. So in future, if we are using different camera images or for the same model, it will perform better. So as we conclude from this work, that this research adopts hyperspectral imaging data from visible to NIR range to demonstrate the application of static regression model for moisture content predictions. Our static regression model also suppresses the state of the art method reported in the literature for moisture content predictions in mushroom. The promising results reveal that the static regression model accurately anticipates the prediction of moisture content with the improved performance matrices such as R-square, MAC, RMAC, MAE, respectively. Our approach and the results confirm that the proposed standard regression model performs the best in terms of performance matrices compared to individual models on the moisture content prediction mushroom data set. We can also use the same model to predict the different parameters of mushroom such as like microbial content, taste, color, and texture. We can also check the generalization capability of a model by using a different data set or different for the different data set or combination of the different fruits and vegetable data sets and make a common pipeline.
Thank you.